Okay, this is problem 9 of section 2.3. The problem is to find two linear transformations u and t from f2 to f2 such that ut equals t0, the zero transformation, but tu does not equal the zero transformation. Okay, so what we want is we want ut of v, which is the same as u of t of v, equals t0 of v, which is the zero vector for all v in f2. Okay, so this means t of v is in the null space of u for all v in f2. Or another way to say this is that the range of t is a subset of the null space of u. Okay, so what we're going to do is we will construct linear transformations u and t so that the range of t equals the null space of u equals the span of, say, the vector 1, 1. Okay, so for example, well, actually, this span is the set of vectors that look like AA, such that A is in F. So we want all the vectors in the range of T to look like that. Okay, so we let T go from F2 to F2 by T of a vector xy is the vector xx, and that's clearly in the place that we want. And we can write that as a matrix 1, 0, 0, oops, 1, 1, 1, 0 times xy. Then T is actually multiplication by that matrix, and that means T is linear, and it's not hard to see that the range of T, the set of vectors that look like that, which is the span of 1, 1. Okay, now we want a transformation u from f2 to f2 so that the null space of u is equal to AA. So that means the vector 1, 1 should be in there. So when I put, or if I put x equal to y, I need to get 0, the zero vector. So one way to do that is to make that x minus y, and we see that when for this to be equal to the zero vector, x must equal y. And this is a linear transformation because it's multiplication by the matrix 1, minus 1, 1, minus 1. So u is linear. And it's not hard to see that the null space is the set of vectors where x equals y, and that's the span that we want. The span of the set of the span of the vector 1, 1. Okay, now we can check that this works. So we check that u times t is the zero transformation. Okay, so we look at ut of xy, which is u of t of xy. T of xy is xx, and u of xx is clearly 0, 0, which is the zero vector. For all vectors x, y in F2, and that means ut is the zero transformation. Okay, so next we show that t times u is not the zero transformation. Okay, so what we're going to look at is tu of the vector 1, 0, which is t of u of 1, 0. So u of 1, 0 is x minus y, which is the vector 1, 1. T of 1, 1 will be xx, which will also be equal to 1, 1, and that's not equal to the zero vector. And so tu is not the zero transformation. Okay, so in the second part of the problem, so part 2, find 2 by 2 matrices A and B such that A times B is the zero matrix, but B times A is not the zero matrix. Okay, so in the first part of this problem, we found two transformations u and t, so that ut is the zero transformation and tu is the zero transformation. So the idea is we let A be the transformation, the matrix of u relative to the standard basis B, and and let B be the matrix of T relative to the standard basis, where B is the standard basis of F2. So this is basically the matrix that does the multiplication. Okay, so what we do is we let A be the matrix 1, minus 1, 1, minus 1, and B be the matrix 1, 1, 0, 0. Then A times B is the matrix 1, minus 1, 1, minus 1 times 1, 1, 0, 0. And if you compute this, we'll get 1 minus 1 is 0, 0 plus 0 is 0, 1 minus 1 is 0, 0 plus 0 is 0, and that's a zero matrix. But when I work out B times A, which is 1, 1, 0, 0, and this matrix, what we'll get is 1 plus 0 is 1, minus 1 plus 0 is minus 1, 1 plus 0 is 1, minus 1 plus 0 is minus 1, and that's not the zero matrix. So we found two matrices A and B, so that A times B is the zero matrix, and B times A is not the zero matrix.